Thank you for giving SPAR5 a go. It was a tough problem set. And thanks also to the jury from Northwest Europe for who put together this contest some years ago. Yeah, hope you enjoyed the problems. We're going to run through some solutions. We'll go roughly in order of difficulty from easiest to hardest. And this will be run by students. So yeah, who wants to talk about G? Fraction, the one where the person is like and most people, most teams solve this problem. Yeah. Have like a PDF. Oh yeah, I have. I can pull up. Yeah, definitely. Right. So far. It's like 12 hours. So we've been done in 3 days. What? It's not good. Medals are up, by the way, for contests. So yeah. Okay.
You know,
So screen sharing. Yeah. So it's screen sharing. You can stop the screen sharing at any point.
Okay, hello. So cool. So the idea of this problem is that you have a.
You can't actually see it by the whiteboard is covered.
Is the microphone even on?
I think the microphone is on, but the speakers are not. If I had to guess, but I'll double check that. And this is a fraction for next time.
Okay, cool. So the problem statement is that you have A, B, A, C, and B, D, and you want to find.
Should be in shot, otherwise.
Then you want to find AT.
Yeah.
So that's like your problem statement. You have ABC, you want to find D. You can do this with like a bunch of triangle formulas. Yep. Okay, cool. So the idea. Okay, so we start by like finding like how big is a small triangle, right? It's half. Let's call that like A3. The small triangle is X. Call that half of DB. And then the big triangle, the whole thing, including the small triangle, is Y. It's like half of A plus D times C. Right, but you can also compute the big triangle by taking the sum of the small triangle, that triangle there, and then the rectangle here. So that's also equal to these.
There is an easier way, to be fair. Yeah, similar triangles. They're similar triangles, so ratio of sides. But this is fine. Carry on.
That's one guess. Yeah, so this is a good equation. You solve for D, and that's your answer. And then to deal with the fraction problem where you have like 100 on 10, and you want to make that simple, you find the GCD of where values divided by that, and it becomes like 10 on 1. That's your answer.
Solution is zero triangles. D on D. A plus D on D.
Yeah, go.
I don't know what that means.
Nick, do you want to go and write it up?
Oh. I'm having a serious problem though.
It's fine. Good. I trust you. I think you're good.
So I think it's this length divided by this length is the same as this length divided by this length. And that's how you solve these.
Yep.
Okay, keep going. What's the name called?
You know. Yeah.
I know we did the area thing.
Nice. Yeah. Well done. That is literally it. Yeah. So similar triangle, solve for D, and then divide out to GCD. Do people know how to find GCD in various programming languages?
GCD.
Yeah. So as of as of recent C++ standards, there's an inbuilt GCD function. In old C++ standards, there is an _ built-in _ GCD in G++. But also it's a one-liner if you want to write it yourself. So like, fine, do it yourself. Python people, GCD is also inbuilt. Great, easy. For what it's worth, it- GCD is something like
Should say what it stands for. Greatest common divisor.
what if B is if B is non-zero, then it's GCD of B and A mod B was it's A, right?
This is recursion.
Huh? Yeah, it's recursive. Yeah. So if B is 0, then GCD of anything with 0 is the other thing. If B is not 0, then we can replace we can replace A with A mod B, because that does not change the GCD. Yep. And yeah, and that just works. If it's so like we're going at this from the perspective of assume A is bigger, but even if B was bigger, then this first step is just going to swap them around, at which point A, the first argument is bigger for the next run, and then recursively this would stay all the way down to the GCD, 0, and return G. Cool. And then you just divide this out of both things. Nice. I believe the next easiest in principle is F. Easier said than done, but a lot of teams did get there in the end. So anyone want to comment on why this one was? It's the calendar one. Yeah, come go. Maybe also just talk about like good habits to like get on right now.
Yeah.
Yeah.
Yeah, so I think conceptually this problem didn't seem to be too hard. It's just like annoying, right? So like basically your problem is you have the leap years that you're skipping. So firstly, the earliest one is 1582. So basically how I counted it is I went from 1700 and just kept incrementing by 100. And then if it was like 400 case, I just ignored it. And then I just compared if the date was there. So the easy way to do that is you can you just look at the Python docs and they have like a datetime library, and like it's literally in the ISO format, so you can just read it in the ISO format, and like then you just have to like they have a delta, so you just add the days, so you just count the days, you do like a comparison with the thing, and then like just add it, and then you get your answer. So yeah, basically someone else solved the whole problem, so you just use the library. There was like an edge case because the library only supported like up to 10,000. So if you're not careful, like actually what I did the first time was I kept checking like 100, and then I had like an invalid date which was like 10,000. So but the thing is that case if you look at the very latest date that they support, which is this one, like that will end in like the 31st of December. So you won't, as long as you don't instantiate it. The other thing you need to make sure you don't do is they can give you February 29th. So that's like an edge case you have to consider, because then you have to count it, but also if you try creating a date as which is that year, you'll get a runtime error because it knows it's an invalid date. So basically what I did is if it was yeah, basic. What did I check? Yeah, I just checked. Oh, I didn't even bother check. You can check like if it's one of the invalid dates and then like -1 and then add 1 to your counter. But I just put it in like a try block because that's the only case where it will have a runtime error. And then in that case, you just like accept it and then like you just minus the date by 1 and then add 1 to your counter when you add at the end. And it's pretty easy if you do it like that. I think if you try and like implement all the addition logic, it's kind of cursed because you have to like. There's so many like edge cases to consider. I don't. Did someone get that working?
There was bugs.
Yeah.
Yeah, I mean, are you just going like, all right, is there anything to contribute here? I don't know.
I don't know.
Yeah, it's just like, Can I suggest another way to avoid the pain, which is there's not that many dates. Yeah, there's 10,000 years into 12 months into 30-ish days. So about what 3.6 million? You can make arrays of that size, that's fine. So literally make an array of every single possible date. I'm pretty sure this will fit.
What are you supposed to return though?
Can you make an
How do you
Like-
get the array?
can you associate to each array the actual string? Maybe not.
To convert the original input into a raw number of days if you want to index into it 5 days past.
Well, but you can search, like you can make an array of all the Julian dates, an array of all the Gregorian dates, and just walk. In principle, fine, but maybe the strings are like a bit too much. Like if you omit the dashes, that saves you like 20% of storage. Maybe fits.
Some sort of bit mask or something with the offense.
You could, yeah, you can.
The addition of days is so easy to do. You
Yeah.
can call the offsets instead.
Yeah,
We did all our calculations in number of days since January the 1st, 1500.
that is the other way to do it. You map Julian dates to number of days since some date, and then count forwards from the Gregorian dates. Yeah, but I think if you just print off the entire thing, it probably should work. There are ways. There's certainly like saving the entire string. I'm reasonably confident works, but you could save just the days, like the day of the month, and then just keep track of the month and the year as you run that loop, and that would definitely work. Cool. Oh, you have 200,000 day. Oh, you have 200,000 test cases. Maybe bad. Maybe you need to binary search. Huh?
You can sort the input and like do it.
Oh yeah, good shot. Yeah, you can do it offline, so that works. But like pain. It's all pain, right?
You can sort them once.
Put once and then put one of the ones you sign.
Yeah. Oh, it's true. Yeah.
You could just like
Wait,
advertise for one index. Like
Oh,
a
yeah.
Why you have
Yeah, I guess like hashing.
Might be in format, that's why.
Okay, I believe the next two are B and C. That's certainly the ones that had the next most solves. In either order. Who wants to talk about B?
You have to do that as well, yeah.
These
are my
Like I actually
Connected, so they like
the recording?
Okay.
No, but like I mean, it's easy enough to. I mean, you can screen share if you want to.
It's what?
Do you want to screen share? Oh no, it's screen sharing.
It's so bad.
It's been screen sharing the entire time, so maybe not all. Maybe stop screen sharing once you talk about the problem.
Okay, so we are given a graph, pretty much. So we're given a bunch of vertices, and each vertex has a number of coins associated with it. And also the graph is connected, and it is undirected, unweighted, and planar, which means that none of the edges can cross each other. And yeah, so we have to find
a click, which is a subgraph that every vertex is connected to every other vertex. Is that correct?
Yeah. Step back.
Step
Just because if you look.
Oh. Oh, okay. Yeah, sure. Okay. So we have to look at all the clicks. So for example, 1500, 1000, 2000 form a click because every node is connected to every other node. And we have to choose the one with the largest sum and output the value of that sum. And the main observation here was that you can't have a click without any of the edges crossing for n greater than 4. So I can do some examples on the board. Yeah. Oh no, this one. This one. Yeah. Don't know if that's visible on the stream, but basically, with 3 nodes, it's quite easy. You just like connect them in a triangle. With 4, you have to get a bit more creative and do sort of a loop around the outside so that none of the edges cross. But with greater than 4, I guess just proof by intuition, you can't really make it work. Yeah, so.
Yeah, now it just becomes a game of finding the clicks. So yeah, for clicks of size 1, it's easy. You just find the max, and then clicks of size 2, that's also not too bad. You deal with this when you read in the edges. So read vertices, read edges. And then now you have 3 and 4 to deal with. You just have a 4D nested loop for each vertex, and then for each 3 other friends of that vertex. If they're all connected, then you calculate their sum and you put it into your ANDs.
So yeah, we go over every node and then consider every triplet of neighbors of that node. And then with those 4, we sum up the cost if they are all connected. So if there's an edge between each of those 4 nodes, then we'll sum the cost and then take the max of the current best value and the cost sum that we just found. And then at the very end, we output the max.
I had some concerns about time complexity when I was thinking about up to 3, and I convinced myself it was fine. And then when I submitted it, it was like, okay.
Does it matter which language you use? Oh, the SPAR one.
Yeah, not necessarily sure what to try.
I don't know why it's like,
Yeah. You can like a spoiler for that, right? Actually, okay, so to do triples, it's like open cubes. And then to do clique of size 4, what you do is you take a clique of size 3 and you pick another node, and then you check whether it's like joinable with the other ones, right? So your complexity to do this is O of n times by clique size 3, right? And then like the maximum number of clique size 3 is just the maximum number of faces if the original graph was planar, right? So if that's true, then you have f minus e plus v is 2. So you have f is 2 plus e minus v. And so I guess e would max 900, and then even if I drop v to 0, you have at most 900 of them, right? So it's like around 900 n. Or it's like of n times 900-ish to do the cliques of size 4, right? So it will just pass. And then yeah.
We obviously otherwise we have to yeah. It's just so
They can see the camera.
No, but if we have a live stream at the same time, it looks good.
Yeah, that's what it means. That's not the stream when you use the board. So maybe
Just like
stop
stop
the
for a second.
Yeah, maybe just stop the stream for a second.
we are not showing. Take a look. Have a gander.
Going once to okay.
It's still recording.
I have to share the screen. I don't share the screen.
Wait, what? Which one was Steve?
Wait.
I don't know if it's still something to look for. We've seen the probability.
What's that back? Okay.
Oh, the part.
What's the card trick? Oh, that's my question. Wait, okay, cool. Who wants to do card trick? If not me.
So the question here was you have these like cards and their faces. So you've got like 2, 3, 5, 3, and Q. And then you've got to find the probability that when someone else starts picking them, they will also end up at this last space. And then the rule is just whatever card you pick, whatever number it has, you skip that many cards and you pick the next card. So you just want to find the probability that they like the second person who does this also reaches the same last space. One observation is that if you reach anywhere in this trail, you'll reach the last face because it's just a fixed path from any sort of node. And yeah, so the way I did it was just a DP. You kind of just have a. Oh, I see. Okay. The way I did it is you just have like dp of I, which represents the probability of reaching this node, and the probability of reaching this node is the probability of reaching I minus 2 times the probability that this card here has a value of 2, plus the probability of reaching I minus 3 times the probability that this card here is a 3, and so on, all the way to 11. You can't have a card of value 1, that's why we skipped this one. Yeah, so all the way to 11. And basically the only sort of like cases we have to worry about is the cards that you've already seen in the first time. The probability of those spaces is always fixed. So in the question that seemed like the first sample was 2, 3, 5, 3, and Q. So those spaces were always fixed. The probability of those spaces was always like that number. And then I think one other sort of little thing I missed when I first coded it was you can have the probability of something being a 10 is much higher than it being like any other number because 10, J, Q, and K all are 10. So the probability of this is 4 over 13, and the probability of everything else is like 1 over 13. Yeah, so you just run that, and then your final answer is just dp of the very last card, the position of the very last card that you wrote. Sweet.
Does that make sense?
Thank you, right on burger.
Does anyone have any more seconds?
But you just like pee and
Yeah, your DP would be like. So if we know what the card is given in the input, then it's just 1. Otherwise, it's the sum of all the future probabilities. Right. How many guys look that? What was it again? It was like
DPI is 0 extra cards, no minutes. The other is not that card. I guess. I plus 10 is 4.
Cool. So it's like the sum of dp of I plus 2, it's like 2 squares ahead of you, times its probability, which is 113, all the way to 11. But 10 is special because there are 4 cards that add to 10. And then, of course, you deal with like range out of bounds. And then your answer should, yeah.
You also have to, I don't know if you said, you have to do the probability of starting at any index between 1 and 10. The typical chance of you starting anywhere between 1 and 10.
Like calculating the final answer.
Yeah, the final answer is, I guess, average of the first 10.
Yeah. So the answer would be like the average of like, oh gosh, PP I to PP of 10. Unless there's like less than 10, in which case you just take the first whatever. Makes sense? Yeah. Any questions? Okay. What's the next question?
What's next?
Yeah, what's the next easy way? I'm gonna like try and not do up groups.
Probably D.
D. What's D? Oh. Based off D. Anyone?
Yeah.
I'm pretty sure that okay, the statement was they give you like this yeah, this like figure where like each next row has like less than or equal to the number of squares as the previous row. And you have to fill it with numbers from 1 to n, and they give you such that like in a row it's non-decreasing and in a column it's strictly increasing. So and the question is a number of ways. I am pretty sure that you can just try it, like or like do it. That's true, right? I couldn't get mine to pass in TLE, so I changed to DP. But I'm pretty sure it's meant to work. So
You need some like groaning and like
Yeah, you did it.
but yeah.
we did it like I put it from the bottom up, and then like I had a count for each value, and then you just do it, right?
Yeah.
Okay, like it wouldn't pass. So yeah, so that idea was okay, like yeah, you have some shape like that. And then like for a particular cell, like we know that the numbers are from like 1 to n. So like let's say the biggest number you put here is n, then you can figure out like the maximum number that will go here, right? Such that you can still put n at the bottom of that particular column, right? So that you can do just by like I guess looping upwards for each column. And then after you figure out a bound for each cell, what you can do is you can just like search through, right? I put mine in DFS. So like I don't know. Like anything recursive, I just do DFS, but like it's fine. So like you do like DFS RC, that fills like up to row R and column C, and you check the cell above you and the cell to the left of you for the value, for the minimum value that you can have, and then you loop from that minimum value up to the cap that you find out, right? And you can put like each of those values in this cell, and then you use DFS to the next cell. And then if you do that entirely, it should work, right? It passed, right? Okay, I just couldn't get mine to pass. But anyway, my code just slow, I guess. But yeah, so like what we ended up doing was given that that didn't work for us, what we did was we did a DP where it's sort of like we did it in columns, and what you're able to do is because there's only like 7 cells in a column, you can like hash that to like a number, and so you can do like a DP of like a column, and then like this like front, where the front stores like the cells that you place in the previous column. and then like you're able to transition that, which is like a bit faster than I guess the combinatorial search, which is meant to like a bit of runs.
Is that exponential short? Wait.
No,
It's
a bit better.
Are you given the column to work out and then the previous column?
Like, it's just the DP.
Oh, in the DP, I believe I didn't implement this. The person that implemented this like left. But I believe it was like DP like yeah, it was DP column, and then you loop through the column that you have, and then based off the front, so the previous column, you're able to figure out what values you can place in your current column, right? And then you do that and then just do the forwards.
And are you returning the?
I thought like this problem has like 3,500 different test cases, so you can like solve it like for every case of life.
That's fair.
And print the answer.
That's fair. Yeah.
Wait, so is front just like 7 digits?
Yeah, I packed them. We packed them in like a 7-digit number, so like 10 digits. It's a state, right? Yeah. So like the.
Oh, no, G.
Oh, yeah. So.
Wait, stop sharing for a second so I can see the board.
I think the next problem is going to be 8.
You want to do A?
I can take it.
Do A.
That's the number.
No, I'm just fixing there's the things.
Like, there's no working diagrams, so I'm like, diagram. Whatever. Alright, if you wait. Okay, cool. Yeah. If you haven't read the question, your inputs are basically for every node. Like, there's a bunch of nodes on a graph, and your inputs are basically the paths, like the lengths of the shortest possible path for every single node to every other node. If I just draw up an example, because like that hurt my brain when I read it for the first time. If this is like node A, B, C, and D, you could have an example graph that looks like, that looks like this, where it's like 1, 2, 4, 5. And your inputs would be like that the distance from A to B is 1. So to be your inputs, your inputs would be all the distances from A to B, A to C, A to D, then B to C, B to D, and then C to D. What?
You're given the shortest path from every node to every other node.
I said that. Okay. But anyway, so in terms of like a solution for this, since you're given all the distances for every node to every other node, what you can do is you can store these distances in like a priority queue that gives you the smallest one first. If I draw out the distances quickly. Yeah, or you could sort them, but we're stupid, or I'm stupid, and I did a minimum priority queue. So what all the distances here would be like, wait, I should have drawn like this test case before I started, but here we are. So like the distance from A to C, that's wait, I did my test case backwards. Whatever. Fuck it, this will still work. 2, and then anyway, yeah. If you sort all your distances so that you have the smallest distance first, what you can do is start constructing your graph. So start off with a graph that has no edges. We know eventually though it should hopefully look like that square, right? And so your shortest distance is A to B was told to be a distance of 1. So you'd be like, so then you'd run like almost like Dijkstra's and be like, can I get to A to B in 1? And you can't, so you draw another edge. And then your next shortest distance was A to D in 2, and you'd be like, can I get to that in 2? No, so you draw another edge. And then the time when the algo changes is like now, right? Your next best distance would have been B to D in 3. But since when you run Dijkstra's, like looking at the next, that next like shortest distance, you can already make it in 3. So you don't want to write another edge there. Because if you do, then you only, it's another part of the problem, right? Is there's only n edges or n roads. So if you drew an edge there, you've like kind of wasted an edge that you need later on. And if you just do, like if you keep going with that algo, you'll eventually draw the answer. That's it. It's just sort these or sort all the distances you're given, smallest to largest, and then run Dijkstra's for every distance. If you can already find if you've already found a path from your 2 points that is shorter than that distance, don't draw an edge. If you haven't, draw an edge. And the only like gotcha with this question that made us waste, I think, 3 retries
is that you will hit time complexity or like TLE. Yeah, you'll time out if you don't like early exit your list of distances. Because if you put every single distance on, it's something like n squared distances that you're then going to run Dijkstra's for. That's pretty bad. But you can, like, the second you've drawn two or like n edges, you can stop. If you end up going through everything and you haven't drawn n edges, which is the case for I think 2 of the examples of the 3 that they gave you, you can just print out any edge on your graph the remaining times. So it looks really weird, but you can just print the same edge in the output over and over again, and that works. Cool. Are there questions on that, or does someone have a better solution? Yeah.
Is this prims or close? I can't remember. But we did the other one to get the minimum spanning tree, and then we got a wrong answer. I don't know why.
I am not sure. I think
Anyone have any like weird edge cases for this?
Wrong answer.
Wrong answer. Yeah.
Wrong answer, not clear.
does Prince consider, but I think you need to do shortest, like when you're following this. Fuck, I had a better test case for this on the paper. Wait, that's not my bag. I can grab it. Like if this is, oh, let me grab a sheet of paper. I drew a test case where you had to do. I don't think.
I get it was like you take the complete graph, you mint that tree, and that's your answer.
And then like check all
We
the,
started with the short, the smallest, right?
Yeah.
And then we kept pushing all the neighbors to the priority queue.
the
So
shortest.
instead of putting every
We didn't do it.
Wait, but when you push the neighbor to the priority queue, do you push?
push like every other node that we haven't seen before.
Because we would be pushing it along with like a cumulative distance, so that you still only do the path.
Yeah.
If you're just were you pushing it like total distance or just like all of the neighbors?
We just take like the shortest edge from all of the neighbors.
Yeah.
And then we push that edge. So shortest edge, that's like one unseen edge, one unseen vertex and one seen vertex.
But if you do shortest edge in general, that won't necessarily find you the shortest path, like unless you're considering like you're like adding up.
Just like think. It should be like some official like number. It might not be the way you. Inserting.
Like what I'm doing to get there, because like the MFP in that square, voltage is assigned to.
Yeah, we do an MST and then to add the last edge, we just do that try and check it.
Did that work?
It worked for all the samples.
So when you do MST, you have like a one here and a 2 here.
Yeah.
You can add a 3, but you should. What I do?
We
That
don't,
wouldn't be.
because it wouldn't be a tree.
Greater cycle, so we.
Yes, that's. Adding a 3 wouldn't be a spanning tree. That's.
The MSC would only consider
Yeah.
you would only do BSC and BSC for the next one. And this is by that would take the shorter one to adding. What's the issue there? Is it right? Does this case work with your argument?
Yeah.
Yes.
We'll look at 3 and then we'll skip it because both B and D are seen.
I think we're breaking case. So we do this time, we do this one. Do you want us to re-walk through the algorithm that we did, or?
Oh, no, we understand it, but we just don't know why our one failed because we also constructed the MSD.
If you write me one case, I can probably, if you still got your code, I can send you the one test case I wrote, because the ones they wrote really fit because there's a like they gave you a graph of with 3 nodes and a graph with 4. Like if you notice in both the graphs with 4 nodes only actually needed 3 edges to be completed. Yeah, whereas so you have to write a test case with like 5 or 6 before you actually start getting into like it picking driven edges.
I've done that. Okay, Eiffel Towers. Oh, okay, moving on.
I don't know.
That's it. I've done that. I've done that. H? No one's off H, right?
That's not very fun. Okay.
Just try every. That's what the cells.
So in I, we have
some expression in Polish notation that's composed of numeric literals and operands. So two operators are the plus operator. So we can have plus AB becomes A plus B. And then we have the minus operator, which has both a binary variant and a unary variant. The problem is the expression that we're given doesn't contain any spaces, so we have a bunch of ambiguous cases, like plus 1, 2, 3 could become either 12 plus 3, or it could become 1 plus 23. And so we're given some expression of this form, and we need to find, based on the interpretation, the minimum and maximum value. Our maximum size of the expression is 1000. So in this case, an O of n cubed algorithm can just pass if you have a small enough constant factor. So what we can do is a bottom-up DP. So at each point in the string, we need to store a set of all of the expressions which can be evaluated at that point.
Miles, can you avoid the very top of the whiteboard because it's extremely reflective and it's getting scored by the light? Yes, so like the left 1/3 is great, and anything from about 2/3 down is great. Yeah.
If we have
and Hugo is going to help as well. Yeah.
plus 1, 2, 3. Okay, that's fine.
Maybe you can just pull it down. Pull the further?
Push it right way.
Okay. Is that better?
Yeah.
Okay. I think like putting it on angle is good. Like putting it on angle is good. Like it's gonna be pretty dark, I think. I mean, we can try. You're not gonna see the board.
You didn't like
It's very dark, right? It looks like a horror movie title. Like, oh,
It's turning on by itself.
Oh wait, that's so good. Yeah. Okay, so now this is like I'm the problem. Okay. But then like as if I can see.
How do you predict it?
Okay, so going back to this expression, at each point we need to store the number of, we need to store the possible expressions you can have from that point. So in position,
Yes.
in position 3, the only expression we can have is 3, and all we need to store about each expression is its value and its length. So here we have 3, 1. And now from 2, there are 2 possible expressions we can have. We can have 2 or we can have 23. And so we have 2 of length 1 and 23 of length 2. Similarly for the 1, there are just the 3 possible numeric values. And then the difficulty comes from when we have either of the operators. So for the plus operator, it's going to have to contain 2 operands, and the first operand will always have to be an expression that starts just after the plus operator. So we can loop over all of the expressions in the index just after the plus operator, and for each of those expressions, we iterate over all of the possible expressions after the end of that expression. So for instance, with 1, first we try the expression 123 of length 3. Just after that is the empty space, so that won't work. So then we try the expression 12 of length 2. Just after that is 3, and that does work. So then that means we can get the expression 15 of length 4 from the plus. And then we try the option where we have 1 of length 1. And then just after that, we iterate over the things from this index with the 2. And the only one of those that works is 23 of length 2. So then we find that we can also get 24 of length 4. So with the minus operator, it's a very similar thing, except you also have to consider the unary minus, where you just have the negative value of the thing. But that's a lot more straightforward than a plus. So the problem is that this can get very large since we're storing a lot of expressions for each index. But the key is that we actually only need to store O of n different expressions for each index, because for some given length L, if we have A comma L, B comma L, and C comma L, where they're in the order A, B, C, there's no reason why we ever need to store B. So once we have determined the expressions for a single index, we just sort them, sweep through, and remove all of the middling ones for each particular length. So now each index stores at most 2n different expressions, because there's the minimum and maximum for each length. And so in the binary operator loop, it's going to iterate over every possible expression for each index, and then every possible expression for the other index, so that becomes n squared. You're doing that n times, so the total is order n cubed, but because it's the sum of a bunch of squares, you get a nice constant factor there, and so n cubed with 1000 does just manage to pass if you optimize. Any questions about that one?
Was it supposed to be a good, or is there any bit?
Which this is I,
Oh,
yeah.
Yeah.
Low.
Like, there's 50 tests, each has 1000 things, right?
50 billion with a constant factor passes. There's a bit for 1 second.
Wait, have you tried like the same solution without eliminating the middle brackets?
Yeah, that was
Okay.
with that one.
So he was like pruning the like that.
Because I think without printing, if you have the case where it's like -0, -0, -0, -0, -0, it can get like exponential.
So there's only 4 solutions that are accepted and none that are multi-tags. And at a glance, it looks cubic. So yeah, I think this is dependent.
Alright. Next easiest one was J, I think.
Yeah.
So in J, you are given some sort of binary tree, which all the diagrams had upside down from the usual direction. And it's like an AVL tree, we want it to remain balanced, where balanced means that the total weight of that for every node that is not a leaf node, the difference in the weights of the subtrees are at most 1, except instead of just being the number of nodes, there are some special nodes that are marked as containing values, and it's the sum of the subnodes with those values that we need to balance. So the maximum size is 1000 leaves, And because it's a binary tree, that implies there are at most 2,000 nodes. And so from the last problem, you might expect that's into your n cubed, but actually we can do better and get it done in n squared. So what we need is a dp of node and sum. And this is the cost to balance the subtree at node with exactly this many with exactly this total score in the subtree at the end. And the way that we define cost is the number of nodes that you need to move out from their original position, because that's always going to be equal to the number of nodes that you place back in later. So we can pretend that placing the nodes back in later is free. And so when we are at a specific node, we know that the sizes of its two subtrees are both going to be sum on 2. If sum is even, and if sum is odd, they're going to be sum on 2 and sum on 2 plus 1. And so if we're at a non-leaf node, we can just try both of these and take the maximum. If we are at a leaf node, it turns out there are very few cases we need to consider. So if we're at a leaf node, if sum is equal to 0, then if it's empty, then, well, we don't need to do anything, we return 0. If it is full, then we need to remove exactly that one object, so we return 1. And then if the sum is 1, then no matter whether it's empty or it's full, either we need to leave it all alone or place a node there. But because the cost we're only considering the cost is removing things, we just need to return 0 regardless. And if the sum is greater than 1, then we just can't fit that many nodes there. So we can always return 0. So in this case, the dp transition is going to be O of 1, and the number of nodes is n. The maximum total sum is the number of leaf nodes on the tree. So this becomes O of n squared, and the solution just becomes dp of the root, and then the total score of the tree. Okay, if sum is greater than 1, we return infinity there, because you can get impossible solutions. The only other annoying thing about this problem was the input is given as a bracket sequence. It's kind of messy to parse, but most languages have some sort of stacked data structure that makes it relatively straightforward. Next is H.
I think so.
I just didn't do it.
That might be loud.
The binary says 4,500.
Right, hold on. Okay. Like, so the idea of H was, you had the cars traveling on highways, and each car left. Okay. I think how it worked was there was a highway, and then each car left here at like some particular time, and it traveled at some particular velocity towards or along the highway. And the idea is that like if a car or if more than one car ends up at the same spot at the same time, then they would crash. So you need to install a new lane, right? So what you sort of think of this as is that like you have like this is the start, and then this is like the end, and at a particular time, at ti, you will have a car that sort of just goes like that, right? And then like at some other time, like let's say tj, you might have like some car that does that, and at like some dx might be something like that. Then you would have like more things like so. And so like what you notice if you draw it like this is basically the number of lanes that you have to build is equal to the maximum number of these line segments that intersect at a particular spot. So in this case, we need to build 3 lanes because for the first 3 cars. And well, like this, you'll need 2 lanes, or the 3 lanes will cover. And so the problem reduces down into a bunch of these line segments, and I want to figure out the maximum number of times some lines intersect at the same spot. And okay, so I'm not sure if this like was the intended thing or not, but I believe that let's say, sorry,
How many lines? Sorry, 35.
35,000. Okay. And was like 35,000.
Yeah, okay.
Like I think mine's like
Wait, what? It's about paths? Should.
I believe
35,000?
it should. Like this line, it's very hard to draw, or like I couldn't
Okay.
draw a
I
case
believe
where
you.
it was like that. Like as in like if I had a thing, or like I know that v okay, like the distance here was 100 as well, and like vi was less than 100. So I guess your gradients go from like 1 to like 1 over 100, right? Yeah, or like 100. Like you only have like sort of like this range that you sort of work with. That it could be it. So like that. So then like I believe that let's say I consider a car, like it is very hard to draw a case where for every single for every single car or every single of these lines, you have a lot of other lines that cross it, and that which at the same time are crossed by like other lines at the same time. Does that sort of like make sense? Like, I couldn't draw a very good case that like does, because like if you had like this sort of a thing happening, you cross this one head on, then like when you move on to like each of those ones, there's like very few like cars that you have to actually care about, I think. Yeah.
The gradient can only go from 1 to 100, so they should go up to.
No, because like you can have multiple cars starting at the same time, which will cause like issues as well. Yeah, I mean, with like different gradients, so like, you can have like more crosses than 100.
But they would only be up to 100 in that school.
Yeah, you can like start like it's just like 10k like cross, I think.
Can there be duplicate cars?
Yes.
Yes.
Which also is annoying.
Answer can be 35,000. Yeah? If
Yeah,
all the
but-
cars are the same time and the same speed, then answer is 35,000. Agree?
Yes.
Yeah.
If all the cars are the same thing.
If all the cars have the same line, so they have the same departure time and the same speed,
Yeah.
then all the lines are like just on top of each other. So then you have to have n lanes.
Yeah, but like that's like fine if I do it like this.
Yeah, I think it's like
one line.
Yeah, but I'm just saying that like
Yeah,
like answer is not done by
Yeah.
or anything like this, right? Because otherwise you could say that for any point, whatever lines go through this point have to have different gradient, and there are only 100 available gradients, so answer is at most 100, but that's not true. Because there can be lines of the same gradient through this.
Yeah, which is like, okay, like supposing this works, how I wanted to do it was, what you can do is you can sweep the start times, and let's say I have a car or a line segment that looks like this. What you can do is, well, the only line segments that can cross this line are the ones that start before it and end after. Right? So like they have to start somewhere here and end somewhere here. So like for instance, a line segment like that. So what you can do is you can like sort by like their start times, and you sweep the start times. And when you're processing each of these start times, you can figure out which range of the previously active cars arrive after like your current car. Which if I put them in a set and you can like lower down for it. And you get the ones that you want. And the idea is that if I intersect them and figure out where they intersect the most, and just take a mass across it, it should work. Added with some annoying details about when the cars start at the same time, meaning that the intersections are at the start, when the cars end at the same time, so when the intersections are at the end, and also you can have like duplicate cars being the same thing. But like I believe the rough idea is like this. Should work, I think. Just implementation details and like floating points. And like, we didn't have time to switch it to rationals, or we didn't really want to like switch it to rationals. But yeah, I think.
So this is n squared.
This should be, well, it's like n squared, but like with pretty good constant factors.
There's no way n squared passes with 35,000.
It's like log n squared.
It's like 1 billion.
That's fine. Okay.
Well, he
Okay.
passed with like 50 billion. So.
Yeah.
No, but yours, wait, was yours like
Wait,
cubic?
like,
It was, wait, it was like,
the starting time is gonna be the same for everyone, and but just modify the like starting point. Then can we do a sweep line on the spine?
Like a vertical straight line like that way.
Like here, everything is starting at like different lines, right? Like, but can we modify that in a way so that it behaves the same?
Things. But I don't think I've found it.
If n squared works, can you just like choose two cars at a time, get like at the exact time that they intersect and keep a frequency table of that, and they just
Yeah, so that's like the n squared, right? Like you take every pair of two cars and then you intersect them and then figure out the max frequency of it. Like it has like a worse factor than this, I believe.
Yeah, the factor is worse, but the rough time complexity is the same. But
Yeah.
I think
I don't think.
this might not be the intended.
Yeah, I vote no.
For each line, you get it, chuck it in hand.
Yeah, but like you can't do that like every pair of lines, right? By doing it this way, you limit the amount of other lines that you have to check for each line. So if you just did it naively, it's like n squared over 2, whereas in this case, I believe it's a lot less than that. Because you can't draw, or I couldn't draw a case where like it did very bad for every single line that you draw.
Yeah, they could only intersect up to 1.
No, you can intersect up to
Everything. Yeah, if you squash it down to like unique lines.
Yeah.
The fattest intersect.
Wait, can you do like two symmetries which does basic update? So the first one will just consider the like sum of areas under the lines. And yeah, and the second one is gonna just consider the ones above the line. And if we add those two, wait, the highest points with the highest sum is gonna be points with most intersections, but I can't say for sure that the highest is the highest.
But like another annoying thing is that like the intersections can be like at floating points, right? Yeah, like the intersections can be at floating points, which is like annoying. Like and others like we were thinking like you can stack it like horizontally and sweep up.
Inputs integer?
Inputs are integer, but you can have cases where like they intersect the floating points.
Yeah.
Like I was thinking like if you had like a point which is like 49, 49.5, something like that. Some 0.5 and then like any odd things, or any even thing would end you at integer places, right?
Yeah. Or in like a register.
What's going on?
Right.
Like you have to like yeah, you have to this is
Yeah, and we were having like precision issues. We're pretty sure.
Yes.
I don't think it was the time, but we only had like yeah, it was like the last 30 minutes, and we didn't want to write up like a rational thing. Deal with it. And you just like swear it in the track. You can code up like a big struct that like does that. Like, but yeah, I believe that. Well, that's the solution that we had, which we
I
thought.
just read the actual solution. It is that.
Oh, it is this.
Yeah.
Oh, okay, sure. So yeah, I find out it is this then.
Oh, okay.
Did I store it with
Is
fractions?
there like a write-up somewhere in that folder or?
Yeah, there is.
Okay, oh, there is. Okay, cool. Sorry. I
Is that like code for it? Like, can you see it? Like,
There's some example solutions.
Yeah.
yeah.
Right, I would have just taken the problems because that's all I need to build the contest, so it's not money. Yeah.
Can you share the link on the sequence of Discord?
So the link to the, wait, so this was in the download from.
Yeah.
Like that's on their link, right?
Yeah.
Yeah, so if you like log back into document, look at the most recent announcement.
Okay.
That link. Yeah, goes to, that's, like, that link, let's find this. Yeah, okay.
What's this? Cool. So just implementations. So
You make this good. So what you're doing in your highway?
Yeah.
This is like.
yeah, so I sweep the start times.
Right.
And out of the alive or like the sweep start times, like you can keep like the sorted end times, right? And so you can figure out the end time of the current one you sweep to, and then what range that is try to intersect it with all of those lines.
So could you just store it in a map somewhere like?
Yeah, you store it in like a frequency things and then just go through it. Yeah.
Because like pairwise, but I'll think.
Yeah.
Okay. How do you think? So the point is, the point here,
Yeah.
So you try off the frequencies of the, you just have to implement some rational things.
Why should you think that
Yeah,
didn't
just-
use that and it didn't see how it's done?
Okay.
Yes, so. What's the next?
E is the only one remaining.
E is the only one remaining. Anyone want to do E? Is the owl one.
Oh, Hayden, I think. So that's.
Yeah.
It's
kind of,
The website itself.
What is it? Okay.
If you log in, it should be there.
Okay, thank you.
Who's talking? About it?
I don't know how it works.
Like another unsolved, right?
well, Hayden solved it. I think, but
Give me a second.
It's like the. There's only one thing.
Wait, no one solved the, like in this room.
The power towers and then you need to.
Vince gonna solve it now.
Want to find how many other T power towers gets you the same. Is it square DP? The 9,000. Wait. Okay, if it's in 9,000. There can be squared, never mind. You want to make the first of the right number you guys possible and provide. You can check the of the bus. Like assuming that
I'll try, but like no guarantee that it's just like.
the off-white one error.
Okay, you could be a same background. Wait, 9,000.
Take 20 seconds. Yeah, let's go.
I'll try and survive. Alright, let's see. I'm gonna try and make my way make sense of it as we go. And feel free to jump in if you have anything. Alright, let's give it a go. Okay, so problem is you're given some power tower, A to the B to the C, and you need to know how many other like how many ways this could be written in this form. You are allowed power towers of at least 3?
Yeah.
Cool. Okay, cool. Okay, if G is yeah, sure. Okay, so how many, like if n has the prime factorization p1 to the alpha 1, p2 to the alpha 2, up to pk to the alpha k, how many ways are there to write this n as a perfect power? Like, when is n a perfect square?
When everything is divisible by 2.
Yeah, when all the alphas are even. When is it a perfect cube? When all the alphas are multiples of 3, etc. So, yeah, so it's the GCD of all the indices, right? 2, right? N A to the power B is GCD of the alpha I. Okay. Why this is relevant, I'm not sure.
I think you're trying to minimize the A so that you can use it on the MC. Maybe.
Yeah, well, I mean, you don't only want to minimize A. You might want to also consider some where A is not minimal. You want all of it. But yes.
Like on the diagram.
Yeah. Okay. So suppose we have this expression. Let G be the GCD of exponents of A. Okay. So this is saying write A in that form that we talked about earlier as P1 to the alpha 1, P2 to the alpha 2, etc. Pk to the alpha k, and let G be the GCD of those powers. Right. So that means that and so if we write if we write this as a perfect power of G, then we can rewrite this as P1 to the alpha 1 over G, P2 to the alpha 2 over G, etc., up to Pk, so Pk to the power of alpha k over G, and all this to the power G. Let's call all of this X. Yep, so this is the smallest base from which we could build the power tower. Yep. Okay. So if I rewrite now the original expression, I can write n as x to the power of g times b to the c. All right. And I know for sure that x is x has like co-prime exponents. Yeah. So you can't get any further down. Right. This x is the smallest base possible. It may be the case that we use other bases as well. All right. Cool. For now, we are going to not worry about x. We're going to work on the exponent, which we are going to call capital B. Right. Now, suppose we knew capital B's prime factorization. So say we had capital B was Q1 to the beta 1, Q2 to the beta 2, etc. up to QL to the beta L. Right? Okay. So this means that any time that I write n as so if I was able to write b capital B as what is the notation they use? U times v to the power of w, then that means n is x to the power of all of this stuff, u times v to the w. Yep. But multiplying powers is the same as kicking one inside the other. So this is x to the u whole thing to the power of v to the w. Agreed? Yep. And so this would be yet another, like this would be a different power term. Yep. So this means that, so this is, so every factor u that I can take out of b, leaving a perfect power, gives me a remaining power tower. Yep. However, actually, this could potentially give more than one power tower because w itself might be a perfect power. Yeah. Which would recursively, yeah. Cool. Okay. All right. For every w greater than 1, w is less than or equal to the max of bk. What is bk? Great, it's not defined anywhere. Wonderful.
Okay. I think it could be like the next step after we choose some like variable u or x.
Yeah. What? Ah, wait. Oh, no, it's the beta case. Okay, cool. All right. Okay, so okay. Let's fix some w that is in the range that we might care about. Okay, we have talked about this. I hope everyone's got it down by now. So let's fix some w that's in the range 1 exclusive to the largest of the beta case. The beta, let's call them j's. Okay. For every prime pk, count the decompositions like this. Right. So how many ways to rewrite? So the term from before that we saw, qj beta j. This is one term in the prime factorization of the big exponent capital B. We want to rewrite this in the form qj to the sum uj times qj to the power of w times vk. Okay, so what this is, vj. So what this is saying is, if I fix a particular w that's anywhere from 2 inclusive up to the largest of the powers that I care about, of course, if I go any higher than the largest of the powers, then this is impossible. Yeah, because there just will be too many powers of qj on the right-hand side and not enough of them. So what this is saying then is, if I take one term of this prime factorization and I split it up into a perfect w's power times some other stuff, how many ways are there to do this? All right. Okay. How many ways are there to do this? Well, in order to solve this, we really just want beta j to equal uj plus w times vj. Yeah. And so if I know a particular, so how many solutions are there to this equation? If beta j is fixed and w is fixed, how many solutions? What do you have control over?
And give out the tangent.
It's like simpler, right? Because we're looking for integer solutions. Yeah. So the only thing we really get to pick is how many copies of w we deduct from beta j before throwing the rest into this remainder uj. Yep. For example, if w is really if w is like very close to beta j, then you'll only have the choice of picking it 0 times or 1 time, right? Vj could only be 0 or 1. Yep. However, if beta j is like 10 times w exactly, then you could make the quotient anything from 0 to 10 inclusive, and each time you can throw the remainder into uj. So actually, the number of ways for this is the ceiling of beta j divided by w plus 1, because you can have 7. Oh. Yeah. Okay. And then repeating this over all the different prime factors, we get the product of such terms. All right. So that's the number of ways to split off some term of. Yeah, hang on. Okay, so remember, we were trying to split off some u and leave the rest to be some perfect power. So we, like, for whatever w that we picked, we had to do this process on not just a particular fixed index, fixed index j in this factorization, but actually on every index at the same time, right? So what this is saying is, of the powers of q1, let's say this is 2 to the power something, 3 to the power something, 5 to the power something, we're saying fixed w equals, let's say, 4. So we want to make a perfect fourth power, and then pick some of the rest. So you have to leave some multiple of 4 power of 2, some multiple of 4 power of 3, some multiple of 4 power of 5, etc., and kick the rest of it into some remainder term. And so these are the number of ways of assembling this remainder term u and making the rest of it a perfect power of, in this case, 4. Yeah. So so if I fix a particular w, the number of ways of splitting up this entire big prime factorization into a perfect power of w times some other stuff, as in this, is the product over all primes of this. Yep. So number of ways is the product for over j from 1 to L of 1 plus the ceiling beta j over w. There is one special case though, because you're not allowed to have the base of this power be 1. Yeah, that doesn't really count as a power tower if the middle thing is 1. So you need to actually deduct 1 from it. Yep. Okay. All right. So what we have done now is worked out the number of ways to split up this exponent capital B into some stuff times some perfect power of w, and I could sum this over the various w's. Yeah. And is that the answer? It is almost the answer. The last thing is that w itself could be a perfect power, in which case we'd have to consider the power towers that are of length 4 or more, and you can do this recursively. Yeah. Yeah. So you need to multiply this by the number of ways you could decompose into even taller towers by decomposing w to itself a power. Yeah. But once you have done that, then the addition over w of whatever quantity you get. This times the number of ways to expose W further is the answer.
Wait, what's the arguments for the recursion again?
Sorry?
What are the arguments for the recursion?
Okay, so right, so this was the number of, like, we have worked out the number of ways to split up B into something times a power. And if, so we are turning this into this, right? Yep. And so it might be the case that W itself can be represented as a power. And so then you think of W like you did B here. Yeah. If W could be written as R times S to the T, then we would have V to the W. Then V to the W would be V to the R to the power S to the T. Yeah. So you recurse with W taking the place of the V. Yeah. Problem is hard. Yeah. I think we're good. Was that all the problems then?
Wait, I think we can even like keep track of like all of the V, W, and U, and even if we like just store it in a map, I don't think we need to visit that many different things.
Maybe.
Yeah.
Yeah, because like you can't have power towers very high before.
Yeah, it's like the height is gonna be up to 10 or something.
Yeah, I'm inclined to believe you. Yeah. Yeah. So maybe there are ways to like pre-compute to like not have to do all of this. Yeah. Or as in like beyond a certain time.
Yeah, but on the solution, like, does it do the DP like on a just array or like net? If it's just array, like, are we doing the first manually?
I'm not sure. I don't have the code in front of me. Actually, not sure. I mean, you can check this yourself, right?
Yeah.
Thank you.
Yeah.
Yeah. This one has a map.
Yeah, I think it's a map. It should be map, I think. Because like it's gonna be quite big.
Yeah.
Yeah, that's like what I was like worried about.
Okay. All right. Look, we're done. Thanks everyone. All right. Let's call it. And yeah, there's a little bit of packing up, but it's like 99% done. And yeah, good night.
I think